Hello everyone and welcome to video 3.1 Thermal Concepts. So here we start out on our usual slide with our data booklet reference Q equals MC delta T, Q equals ML. Since this is section 3.1, you're going to find those formulas in box 3.1 in the data booklet. So it's on the next page in the top left. We've got just those two formulas right there. Okay, so let's go back to the slides. We're going to skip this stuff. It's IB. And here we go. Let's talk about some molecular theory of solids, liquids, and gases. So the three main states of matter, or phases of matter, are solid, liquid, and gas. There are other states of matter like Bose-Einstein condensate, plasma, but we're not going to be studying that here. I believe in chemistry you look at the Bose-Einstein condensate. So in a solid, particles actually do move. It's not as if they're not moving. In a solid, they move, but they just vibrate, so they can't translate. Vibrate just means they move back and forth. Okay. In a liquid, the molecules can vibrate, but they also can move around freely within a certain fixed volume. Okay, now, when you go from a solid to liquid, some of these intermolecular bonds get broken. Not all of them, but some of them. And when those bonds are broken, it gives those particles more energy to move around. When you go from a liquid to a gas, most of those intermolecular bonds are broken. Hence, the gas particles have a lot of energy, specifically kinetic energy. Okay, phase change. So instead of saying state of matter, we're going to start saying phase. When you go from a solid to liquid, we know that that's called melting. When you go from a liquid to gas, that's called boiling. Now, each of these processes can be reversed as well. So let's look at all of these processes and find out what they're called. Okay, so solid to liquid, that is melting. Liquid to solid, that is freezing. Liquid to gas, that's boiling. And gas to liquid, that's condensing. Solid to gas, that's sublimation. And gas to solid, that's deposition. Now, those last two are probably the ones that you're least familiar with. How can a solid go directly to a gas? Well, if you've ever opened up your freezer and you have a tray of ice cubes there, you've probably seen this vapor around the ice cubes. That is sublimation. It's the solid ice cube turning into essentially water vapor within the freezer. And frost developing outside on a very cold day, that is the gas turning into a solid directly. All right, internal energy. This is going to be a very important concept that we're going to keep referencing over the next several slides. Now, we know that all substances are composed of individual molecules, and those molecules vibrate. Now, when you heat a substance up, it becomes more energetic, so it increases its kinetic energy. But as things heat up, we also know that they move further apart. And when they move further apart, this actually increases the potential energy of the substance too. So what we see is that by heating up a substance, you not only increase the kinetic energy, but you increase the potential energy too. And so together, the kinetic and potential energies of the substance, it's called internal energy. Okay. So E internal is equal to E kinetic plus E potential. So here we go. Here's a nice visualization. Total internal energy is made up of kinetic and potential energies. Now, kinetic, this is due to vibration and translation, potential intermolecular forces. We're not going to get into this too much. This is really just getting the tip of the iceberg here. You're going to be studying this stuff a lot more in chemistry, as I know. All right, now we know that we can add heat to a system and it'll have more kinetic energy. Now, when you add heat, sometimes the thermometer shows an increase in temperature. Not always, as we'll see in some later slides. Now, something to understand is that the thermometer measures the internal kinetic energy of the substance. Okay, now, potential energy has a slightly different analogy. Now, in the slides, it tells us to think of something called Hooke's law, and we've got some atoms and springs between them. We don't learn about Hooke's law or springs until grade 12 physics, so please just ignore this for now. All I need you to know is that there is total internal energy represented by potential energy and kinetic, and that thermometers measure internal kinetic energy. Okay, now how do we measure temperature? Well, we use a couple of scales. A lot of people will use thermometers. Thermometers used to be made with mercury inside, but because a lot of them would break, since they're made of glass, the mercury would leak out and it's highly toxic. And so now thermometers are made with other substances. Now, whatever the thermometer is made out of, it is usually calibrated with water so that it shows you the freezing point at 0 degrees Celsius and it shows you the boiling point at 100 degrees Celsius. Okay. Now 0 degrees Celsius is 32 Fahrenheit, 100 Celsius is 212 Fahrenheit. We don't really need to care about the Fahrenheit scale. We really are going to worry about the Celsius scale and a new unit of measuring temperature, which we'll be introduced to shortly. Okay. Remember, temperature only reveals to us the internal kinetic energy. Expansion reveals internal potential energy. Okay, so the more separated the particles are, the more potential energy there is. Okay, let's look at the following scenario. Okay, we've got a heat source on the bottom of this box. Now, inside of this box, we've got a thermometer and we have a pressure measuring device. So we're going to be plotting the pressure versus the temperature in degrees Celsius on this axis. So pressure versus temperature. Now notice the temperature went up and the pressure went up on this gauge. So we plot our first point right here. Don't worry about the scale here. We're just doing this relatively speaking. As more heat collects inside of this chamber, the temperature goes up again and the pressure goes up as well. So we wait a little bit longer, the temperature goes up again and the pressure goes up as well. One more data point, temperature went up, pressure went up. So they both went up together. Now with 4 data points, we have more than the required amount of data points to plot a line of best fit. And in fact, we're going to do more than that. We're going to plot a line of best fit and extrapolate it. Okay. The word extrapolate means if you have a set of data points and you want to draw a line of best fit through them, that's great. But if you want to get more information than what's currently in your data set, you extrapolate. So if I just wanted a line of best fit, I might just go to the p-axis, or I might just go from one point to the other. Okay, so extrapolation means I use this line of best fit and I extend it to the left and I extend it to the right so that I can gain more information, assuming that the same pattern is followed between pressure and temperature at these ranges. Interpolation, on the other hand, means obtaining data values between the data points that currently exist. Extrapolation means obtaining data points outside those that currently exist. So this is why we extended the graph all the way down to the p is equal to 0 or t-axis. Now we're going to do the same thing with different gases. So if the same experiment is repeated with different gases inside of this chamber, these are the points that we get. So this is a different gas, and if you extrapolate those points with the line of best fit, we get that blue line. And if we put yet a different gas inside, we get the following 4 x's. Again, drawing a line of best fit and extrapolating it, we get something like this. Now, something really interesting is that all 3 of these lines intersect the t-axis at the same point, some point between -200 and -300 degrees Celsius. So at that point, all 3 of the gases result in a pressure of 0. And yet when you increase the temperature, all of them increase pressure linearly, but at different rates. But why do they have the same temperature at 0 pressure? So think of it like this. Remember we said that even for a solid, the particles are moving, but they're vibrating. Now when things get colder, they move less and less and less the colder they get. Now if you make them very, very cold, it'll get to a point where they don't even exert any pressure against the walls of their container. So pretend the gas is inside a container. If it even has a little bit of kinetic energy, those particles hitting the walls of the container will cause some kind of pressure. But if they move less and less, there's less and less pressure. They're hitting the walls of the container fewer and fewer times. Now it'll get to a point where the pressure will actually reach 0, when they don't hit the walls of the container at all. And this occurs when the particles themselves fully stop moving. And we can see based on this graph that no matter what type of gas we have, this 0 movement, 0 pressure occurs when the temperature of the gas reaches -273 degrees Celsius. And that is the temperature for all gases at the point at which they stop moving. Specifically, it's -273.15 degrees Celsius. Now, when scientists learned this, they had 2 options. Either they could stick with the Celsius scale in science, which sometimes they do, or they could start a new temperature measuring system called the Kelvin. So if this is the lowest temperature, and it is, we'll see on this slide, this temperature right here, -273.15, it's called absolute 0 because it is the lowest temperature in the universe. But it's given such a weird number, -273.15. It would have been so much easier if 0 of some temperature measuring scale was the lowest temperature, and the higher temperatures would just go above 0, and there would be no negative temperatures. And so hence the Kelvin temperature scale was invented. So the Kelvin temperature scale tells us that the lowest temperature in our universe is 0 Kelvin. 0 Kelvin is the same thing as minus 273.15 degrees Celsius. So this is how we convert between Kelvin and Celsius. Okay, so we have absolute zero down at the bottom, and we have freezing temperature on the top. This is just relative, so you can see that, well, if the gauge on the thermometer goes up, the temperature is increasing. So absolute zero is 0 Kelvin, or minus 273 degrees Celsius. A lot of times the two decimal places here are ignored. Freezing point is 0 degrees Celsius for the Celsius scale, and it's 273 Kelvin for the Kelvin scale. Notice that for Kelvin, we don't say degrees Kelvin, we just say Kelvin. Okay, so make sure you don't put the degree symbol or say degrees. Okay, this is the relationship between Kelvin and degrees Celsius. Whatever temperature you have in Kelvin, whatever temperature rather you have in degrees Celsius, add 273 onto that and you'll have the temperature in Kelvin. Or if you have the temperature in Kelvin, subtract 273 from that and you'll have the temperature in degrees Celsius. That's really all it is. Okay, so for example, convert 100 degrees Celsius to Kelvin and 100 Kelvin to degrees Celsius. So we'll do this one right on the slide. It's pretty simple. If you have 100 Celsius, so that would go in this slot right here. And I should point out, this is not on your formula booklet. You should just understand that this is the conversion. The best way to remember this is just remember that absolute zero, 0 Kelvin, is minus 273 degrees Celsius. And then you can convert however you like. So if we have 100 Celsius, we add 273 and we get the temperature in Kelvin. So 100 Celsius is 373 Kelvin. If we have 100 Kelvin, that would go here. We would subtract 273 from that and we would get minus 173 degrees Celsius. All right. Now, in the United States, generally heat is measured using calories or kilocalories. We don't even, I'm not even going to bother with this because we are not in the States. We don't need to worry about kilocalories. So I'm just going to go ahead and skip this. Although there is an interesting fact here that in Europe, they don't call it low calorie soda. They call it low joule cola. So that's pretty cool. But we're going to go ahead and skip this. So skip these slides. Skip this. If you're interested, you can learn about calories and joules of energy. That's fine. But I'm not going to test you on this. But here we go. This is where we're going to continue. Specific heat capacity. Now, every material is different in how it can absorb heat energy and what temperature it will arrive at. Imagine you have two pots. One is full of 2 liters of water and the other is full of 2 liters of chili. If this is making you hungry, I apologize. So if you put both of them on equally sized burners and you put both of the burners on the same temperature, so you're trying to heat it up, let's say you put them on medium or medium-high heat. Over the course of the next 3 minutes, both pots, both substances will have absorbed the same amount of heat energy. But if you were to stick a thermometer inside, they will have reached different temperatures. If you had to guess between the chili and the water, which one will come to a boil first? If you guessed water, you would be correct, right? Because water, well, it's going to be, there's less density there compared to the chili. The chili has water, it has meat, it has beans, it has tomatoes, it has a lot of stuff. So it's going to take longer to heat up. But it's not just the density of the material that determines how long it takes to heat up. And in fact, sometimes denser materials take less time to heat up. A lot of the time, it just depends on the material and its ability to absorb heat. So what we're going to be looking at is materials that have mass M. They're going to be absorbing heat, symbolized by the letter capital Q, and they're going to change in temperature, delta capital T. Now, because every substance has a different ability to absorb heat, we call that ability to absorb heat the specific heat capacity, and it's represented by lowercase c. All right, so it's the amount of heat needed per unit temperature increased per unit mass. Something interesting to think about when discussing specific heat capacity is this. We know that the further you are away from the equator, the colder it gets, right? Countries around the equator are relatively warm. But if you look at Australia, which is in the southern hemisphere, and you pick a point equally north above the equator, chances are that the point you picked north of the equator is a little bit colder than the point you picked in Australia. Okay, so if you pick the southernmost point in Australia and pick somewhere north of the equator at the same distance, you will find that the country on the north, or the location you decided with on the north, is much colder. But why is that? So think about that for a moment. Just why would that be? It has to do with land and water. If you look at the globe, when you get a chance, pull up a map of the globe, you will see that in the southern hemisphere, there is substantially more water than there is in the northern hemisphere. So the water to land ratio in the south is greater than the water to land ratio in the north. Now, water absorbs heat at a different rate than land. Water can absorb heat and it can retain it. Land, on the other hand, cannot absorb as much heat as water. And so because the water can absorb so much heat in the summer, over the course of the winter, it will slowly release it, keeping milder temperatures in the winter for Australia. But because we have more land mass in the northern hemisphere, we don't absorb as much heat during the summer months, which then get released during the winter months. Hence why a point south of the equator is warmer than a point equally distant in the north side of the equator. Here is the formula for measuring the amount of heat energy in joules, okay? The amount of thermal energy that either makes some kind of transaction or transfers from one object to another. It's the mass times specific heat capacity times change in temperature. Now, the C value that we're going to be using is going to be joules per kilogram per degree Celsius. So that means that delta T will be measured in degrees Celsius, M will be measured in kilograms, and Q is, of course, measured in joules. If you guys study chemistry, you'll most likely see this formula again, and more often than not, the M will be measured in grams because you'll be dealing with smaller masses. Now, each material has its own specific heat capacity. So in the case of Australia versus a point equally distant above the equator in the north, the specific heat capacity for water will be much higher than that of land. Okay, so actually let's look at some values here. Okay, so we've got air at 50 degrees Celsius, water at 15, steam at 110, ice at -5, wood, ethyl alcohol, and steel. Now notice that for air, so let's look at the units here first of all. These are the specific heat capacities, joules per kilogram degree Celsius. So what this means is, for air, it takes 1,050 joules of energy to raise the temperature of 1 kilogram of air by 1 degree Celsius. Similarly, well, look at this, for water is much more. It takes 4,186 joules of energy to raise 1 kilogram of water by 1 degree Celsius. Now, that will probably make common sense to you because water is a lot denser than air. But then go down to the bottom and there you got steel. Steel is incredibly dense and made mostly of iron. And yet, it only takes 460 joules to raise 1 kilogram of this by 1 degree Celsius. So it's not just density that is a factor, it's also the composition. Right? So there's a whole lot of things involved here. All right, so we have Q equals mc delta T. Air has a density of about rho. So this funky looking P symbol is rho. I'll draw it on the sheet. I'll show you how to do it. Equals 1.2 kilograms per cubic meter. How much heat in joules is needed to raise the temperature of the air in a 3 by 4 by 5 meter room by 5 degrees Celsius? So I hope you have the slides in front of you. We're going to go to our page here and we're going to solve. Hang on a sec. Let me focus this. Perfect. There we go. There's a lot of light coming into the room, so I think it's losing its focus a bit. All right, here we go. So density. This funky looking P symbol is the Greek letter rho. So yes, you are going to learn a whole new alphabet this year in addition to learning physics. Rho is the symbol used for density. Okay, so rho is 1.2 kilograms per cubic meter. The room has a volume of length times width times height, and it's 3 meters by 4 meters by 5 meters. So actually we can just do that calculation on the spot. Let's just do it like this. 5 times 4 is 20, 20 times 3 is 60. So that's 60 cubic meters. So there's the volume. Now, what does density and volume give you? Well, density and volume give you mass. Okay, so density is mass per unit volume. You can see it in the units, mass per unit volume. So if I'm looking for mass, rearrange this formula, it's density times volume. So density is 1.2 kilograms per cubic meter times 60 cubic meters. Make sure the units are the same, which they are. 1.2 times 60, we get 72 kilograms. Okay, and that's exactly what we need. All right, so we have the mass. We know that we want to raise the temperature of the air in the room by 5 degrees Celsius. Because the specific heat capacities in the table on the previous slide were given in degrees Celsius, we don't have to convert this to Kelvin. Okay, so we want to know how much heat is required. And since it's air, I'm going to go ahead back to that slide. So let me just pop over back to the slides for a moment. Let's look up the specific heat capacity of air. So air is right here. So 1050 joules per kilogram degrees Celsius. 1050. Okay, so remember that. So C is equal to 1050 joules per kilogram per degree Celsius. So that looks really weird written like that. If you want to write it as a fraction to make it look easier, just go ahead. That's just really strange. Joules per kilogram degrees Celsius. It'll be easier to cancel out units like this. Okay, so we need Q. So Q is equal to MC delta T. And so we have 72 kilograms. I'm writing the units this time so you can see how everything cancels out nicely. Times 1050 joules per kilogram degrees Celsius times 5 degrees Celsius. So we can see that the degrees Celsius cancels out, the kilograms cancel out, and we're left with joules, which is the unit for heat. This is effectively the thermal energy that I kept talking about in the previous unit. So 72 times 1050 times 5, 378,000 joules. So I mean, I can leave it like that, 378,000 joules, or I could even call this 378 kilojoules. Either one of these is fine. It just looks cleaner to have the bottom one. Okay, back to the slides. All right, so we're not going to need this, or we might actually, but let's see what happens. Okay, next. Suppose we have a 200 kilogram steel ingot and a 200 kilogram block of wood, both at room temperature, 20 degrees Celsius. By the way, an ingot is like an oblong, elongated piece of metal, like steel. A picture of it will come up after this. If we add 1,143,000 joules of heat, the energy of a Snickers bar, to each object, what will its final temperature be? Okay, so we have, let me just put that picture up. There it is. There's a steel ingot. Let's go back to our sheet. Okay. So we've got two materials here we got to keep track of. We've got steel and we've got wood. Okay, now the steel and the wood are both 200 kilograms. So mass, 200 kilograms, mass, 200 kilograms. And that's the unit we need as well, so that's fine. They're both initially at room temperature, so T initial is 20 degrees Celsius. T initial is 20 degrees Celsius. We're adding the same amount of heat to each object, so Q is and I'm changing this to scientific notation, by the way, 1.143 times 10 to the 6 joules. Q equals 1.143 times 10 to the 6 joules. What will its final temperature be? So T final. Now, anything to do with temperature, if I need to find T final, that means I have to find delta T for both. Okay? Because once I find delta T, I just set delta T equal to TF minus T initial, and I have T initial, hence I can find TF. So there's only one piece of information missing here, and that is the specific heat capacity of steel and the specific heat capacity of wood. So if it's not given to you in the question, it is assumed that you know where to look it up. So let's go back to our slide and let's look it up. Let's go to that table. Okay, so steel, it's right here, 460 joules per kilogram degrees Celsius. And I realize you can't see what I'm writing right now, but you'll see it afterwards. Specific heat capacity of wood is 1680. Okay, so let's go back to the question. And there we go. think it was 1680 joules per kilogram degrees Celsius. Okay, that's it. So we just need to do Q equals MC delta T, and we're going to rearrange this for delta T, so that's Q over MC, so that's 1.143 times 10 to the 6 joules divided by 200 kilograms and 460 joules per kilogram degrees Celsius. I've already verified that all the units match up, so I'm not going to bother to write the units in this time. So 1.143 times 10 to the 6 divided by 200 times 460. 12.4. So 12.4 degrees Celsius. That's the change in temperature. So delta T is 12.4. So let me just bring this back up here. So delta T is equal to T final minus T initial. So T final is equal to delta T plus T initial. So that's delta T, 12.4 plus 20, that's 32.4 degrees Celsius. Okay, so the final temperature of the steel is 32.4, and for wood, okay, so here we go. So delta T is equal to Q over MC, so 1.143 times 10 to the 6 divided by 200 times 1680. 1.143 times 10 to the 6 divided by 200 times 1680. 3.4. Wow, so this one barely changed in temperature, whereas this one changed a lot in temperature. So the wood really didn't change much. I mean, and this is another way for us to see that steel, or in most cases metal, they're good thermal conductors, but wood, it's a thermal insulator. I mean, it barely increased in temperature with all that energy added to it. So now we're going to use this expression. So TF is equal to delta T plus T initial. And the only reason I'm jumping to this formula is because I already arranged it here. So delta T is 3.40. Initial temperature is 20. So you have 23.4 degrees Celsius. So wow, what a difference. 32.4 versus 23.4. And that's actually interesting. It's just the first two numbers rearranged. So you can add the same amount of energy to two different objects and they will end up at two very different temperatures. Thermal insulator, thermal conductor. Okay, this is why when you cook, you want your handles made out of wood or some other kind of insulator. Definitely not metal unless it's somehow not connected directly to the heat source, if there's some kind of insulative material in between. Okay, so that's that. All right, sketching and interpreting phase change graphs. So this is going to be a huge part of the next part of this lesson. A phase change graph or phase change diagram is kind of the same thing. So really what this diagram is going to communicate to us is if I add a certain amount of heat over a certain amount of time to a substance, how does the amount of energy in it change, right? Or how does the temperature change? What phase changes take place and when? All right, so assume we have a thermometer that's frozen in ice. Then the ice is cooled to a further minus 20 degrees Celsius. Now we're going to slowly add heat. So we put a heat source on the bottom and the time is elapsing. And we're going to plot the temperature versus heat added. So right now we're at minus 20 degrees Celsius and we're adding heat. So what happens? As we add heat, the temperature increases until we hit 0. Once we hit 0, now the ice can melt. But heat will still get added until all of the ice melts into water. And until all the ice finishes melting into water, the temperature remains at 0 degrees Celsius. Once all the ice has melted into water, now the heat that's added can go towards, oh, sorry guys, for some reason, oh, it's going backwards, my apologies. Okay, once all the ice has melted into water, the heat can now go towards heating up the water until it reaches the next significant point, which is 100 degrees Celsius. At this point, the added heat will slowly change the water into a gas. It'll evaporate, right? But the 100 degrees Celsius temperature will stay until all of the water evaporates into water vapor or steam. And so no matter how much heat still gets added, the temperature will remain constant until it reaches that new next boundary. So then as you keep adding heat, the temperature will just keep increasing past that point. Oh, sorry guys. Let's actually plot it. It'll be a lot easier to see once it's plotted. All right, so on the horizontal axis I have Q. This is the amount of heat added, but a lot of times this is just replaced with time, because the more time that elapses, the more heat that gets added. So this could just be replaced with time. Okay, and on the y-axis we have temperature. So initially we start off with ice, and it's at minus 20 degrees Celsius. So we start off with a negative temperature. Now, as time goes on and heat's added to the system, the temperature slowly becomes less negative, until it hits 0. Now, like I said, once the temperature hits 0, now the ice can start melting into water. But heat is still getting added to the system. But as long as it's in a phase change, the temperature will remain at 0 degrees Celsius until all of the ice melts. So this dashed line, horizontal line, shows us that the temperature is constant, even though heat is still getting added to the system. And throughout this entire process here, the ice begins to melt, and at the end, all of the ice has fully melted to water. So once we have fully water, now as heat is still getting added to the system, temperature can start to go up again. Okay, so it'll start to go up and up and up. And this will continue until the next critical point is reached, which is 100 degrees Celsius. Once 100 degrees Celsius is reached, we've reached the boiling point of water. Okay, at this point, the water is going to start to boil. It's going to start to become steam. Now, heat is still getting added to the system, and as it gets added, the temperature remains constant at 100 degrees Celsius. It cannot go up until all the water has boiled. So at the beginning of this graph, here, this is when the water starts boiling, and at the end, this is where all of it has finally become steam. So once all the water has become steam, now the heat that still is getting added to the system can finally be going towards increasing the temperature of the steam. And so we have this very interesting looking graph now. Remember that the thermometer measures kinetic energy. And since in the slanted, we'll call them slanted, during the slanted parts of the graph, there's no phase change happening here. This is where the kinetic energy is being added, and that's why the temperature changes. But during the horizontal plateaued parts of this graph, the temperature is constant, so the kinetic energy is remaining constant. That means all of the energy that goes into the system is going into the form of potential energy, right? Because we're changing the bond structure. Remember that internal energy is comprised of kinetic and potential energies, right? So either the internal energy will go towards changing the kinetic energy, or it's going to go towards changing the potential energy. Okay, so we can see again, potential energy, phase change, kinetic energy is when the temperature actually starts to increase. Now, something to keep in mind is we just learned about a very, useful formula, Q equals mc delta T. When a material of mass m in kilograms with a specific heat capacity C gets a heat amount added to it Q, measured in joules, we know that there's going to be a certain temperature change involved. And so if you think about it, that formula, Q equals mc delta T, pertains to these slanted parts of the graph. That means we need another formula to represent these flat portions of the graph. And of course, there's the freezing and condensation point if you're going in the opposite direction. Okay, let's look at this from a different point of view. This is often an analogy that's used in a lot of physics explanations, and it's a particle trapped in a well or captured in a box. Okay, so this particle has some energy, so it vibrates back and forth, but in order to escape from this well, it needs to have a lot more energy given to it in order to change phase. Okay, so when you add heat to the system, this particle stores it as potential energy. So it's able to store more potential energy and more potential energy and more potential energy. And you can start to see why this is such a nice analogy. If you're in a well and you have more potential energy stored inside you, you can be, theoretically, you would be located higher from the bottom of the well, right? Because potential energy is mgh. So the more distance you have between yourself and the original reference line, the more potential energy you have. So the more heat that gets added to the system as time goes on, the more potential energy there is. And if you keep adding the potential energy, at a certain point, the particle will finally break free and escape. Okay, let's finally talk about that heat energy that occurs at these horizontal plateaued parts of the graph. We call this latent heat because it really is hidden heat. The word latent means hidden. And the reason we go by this name is because of the following reason. Throughout these horizontal portions in the graph, we know that heat is still being added to the system. And yet, when you look at the thermometer, the temperature is held constant. Our intuition tells us that when heat is added to a system, the temperature should keep going up. So how can temperature remain constant if heat is getting added to the system? And we saw the reason why. The reason why is because the heat is going towards the potential internal energy, not the kinetic internal energy, which measures temperature. So if it's going to the internal potential energy, we won't see it. We won't see it as a change in temperature on a thermometer. Hence, it's quote unquote hidden. So we define something called the specific latent heat, capital L, by this formula. Now, specific latent heat, capital L, if you rearrange this, it's Q divided by M, the amount of thermal energy divided by mass. So this Q is the amount of thermal energy added along these horizontal segments of the graph. The other Q, MC delta T, is the amount of heat added during these slanted portions of the graph. Something to point out also, since there's no temperature change for latent heat, there's no delta T in the formula. And that's how you're going to tell the difference. If there's a temperature change, you use Q equals MC delta T. If no temperature change, you use Q equals NL. And these L values you can look up, just as you can look up the C values for the specific heat capacity. Okay, now we saw that there were two plateaus, two horizontal segments. That means there are two types of latent heat. There's latent heat when you're going from solid to liquid or liquid to solid. And there's another latent heat when you're going from liquid to gas or gas to liquid. Okay, so when you're going from solid to liquid or vice versa, that's called the latent heat of fusion. Okay, so symbolized by L subscript F. If you are going from liquid to gas or vice versa, that is called the latent heat of vaporization, or L subscript V. And there it is in the notes as well. So let's look at this. For water, we have a huge latent heat of fusion. Okay, so the amount of energy per kilogram of water while you're changing states, it's huge, 3.33 times 10 to the 5. Compare that to mercury, oxygen, and gold, which are much, much smaller. Okay. And if we look at the latent heat of vaporization, water once again has the highest amount. But what's interesting is gold is not that far behind. Compared to gold's latent heat of fusion, its latent heat of vaporization is enormous. Okay, so here it is on the graph. Latent heat of fusion is from one segment to the other, the horizontal piece, and the latent heat of vaporization is on top. And remember, that's for solid to liquid or liquid to solid. Vaporization is from liquid to gas or gas to liquid. Okay. Now let's compare boiling and evaporation. Now, when something's boiling, that means the entire liquid is at the same temperature, hence the boiling point. But evaporation, so when the liquid turns into steam, that only occurs at the surface of the liquid, and that really can occur at any temperature. Now, how can you enhance evaporation? Well, you can increase the surface area. So if you have a cup of water and you pour it into a frying pan and try to boil it versus a very small, narrow diameter saucer, it's going to evaporate much faster in the large frying pan because there's more surface area. So you can increase the surface area, you can warm the liquid, you can have more air movement on the surface. All of those things will increase the evaporation. But what's interesting is that boiling and evaporation both remove the same amount of heat energy from the liquid. Now, some people claim that they actually do feel cooler when they sweat. This is, after all, why we sweat. Maybe another way I should have said that is some people claim that when they drink tea, they feel cooler. Now, personally, on a hot day, if I'm sweating, I don't want to drink tea. I want to drink something cold, like a nice ginger ale. But anyways, this is the fact. This is the way it is. Maybe we don't feel it, but we actually are physically cooling down. Okay, let's try this. Wow, now that's a nice cool chair made of ice. So Bob has designed a 525 kilogram ice chair. How much heat must he remove from the water at 0 degrees Celsius to make the ice chair, also at 0 degrees Celsius? So in this case, we have water. If you add heat to water, it's going to become, well, warmer, and it potentially is going to become steam, a gas. But if you take heat energy away from it, it'll get cooler and cooler and hopefully eventually become ice. And so that's what we're trying to do. We have water at 0 Celsius. It's already at the temperature required to freeze. And so now we just have to make sure that all of it freezes. Let's go to our piece of paper. Oh, we lost focus again here, so let's focus. Perfect. Okay. So we have 525 kilogram ice chair. So if I have 525 kilograms of ice, that means I have 525 kilograms of water. So right now, all of this is in the state of water at 0 degrees Celsius, and we have to change this to ice, also at 0 degrees Celsius. Okay, so no temperature change involved. That means this is a pure phase change question. Now I do always like to write what state to what state it's going. So this is going from liquid to solid. Liquid to solid means we're doing fusion. Okay, so since we're doing a pure phase change, that means we're only considering latent heat. And specifically, since it's fusion, we're doing latent heat of fusion. So that means I have to look up the latent heat of fusion of water. So let me go back to the slides. We did have a table with all that information. Here we go. Latent heat of fusion. So you see, if you accidentally get vaporization, your number is going to be way too big. So 3.33 times 10 to the 5. 3.33 times 10 to the 5. Oops. 3.33 times 10 to the 5. And the units are joules per kilogram. After all, the formula is Q equals mL. So L would be Q divided by M. So we have to find out how much heat we need to remove. So Q is the amount of heat. So if that's equal to M times L, well, it's a 525 kilogram chair and a latent heat of fusion. It takes 3.33 times 10 to the 5 joules of energy per kilogram to change the phase of water into ice, and ice into water technically. 525 times 3.33 times 10 to the 5. 174, 825, 000. Wow, that is a huge number. 174, 825, 000. Wow, yeah, that's right. Okay. So we're going to call this approximately 175. Now, I could say this is times 10 to the 6. That's joules. Joules times 10 to the 6 is mega. So I'm just going to call this 175 megajoules of energy are required to do a phase change of 525 kilograms of water to ice. Okay, let's go back to the slides. The last concepts we're going to look at in this section 3.1 are the 3 ways in which radiation can, or rather heat, can be transferred. And those 3 methods are conduction, convection, and thermal radiation. Now, thermal radiation really, I mean, light is an example of radiation, heat is an example of radiation, the microwaves in your microwave is an example of radiation. Now, radiation traveling through space that makes you feel warm, that's due to something called infrared radiation or infrared energy. Okay, so the interesting thing about energy from light or electromagnetic radiation is that it can travel through space. So radiation, even thermal radiation, it doesn't need a medium. It can just travel through space. You can even travel through a vacuum. Conduction. Conduction is when heat transfers from one solid object to another when they touch. So while there is no medium of transfer required for radiation, there is absolutely a medium of transfer required for conduction. So this is essentially what happens. Imagine you have particles and you have something very hot on the right and something very cold on the left. Eventually, these particles, through vibrations, will transfer the heat energy from the hot object to the cold object until both sides are at the same temperature. So, hang on a sec. Unfortunately, guys, the animations are still not working. Okay, so I'll just have to describe it for you. Imagine these particles start vibrating, and their vibration gives these particles energy. So these start vibrating, and then the vibration of these particles cause the next ones to start vibrating, and then the next ones, and then the next ones, kind of like the fall of dominoes, right? So as the energy transfers, it gets a little bit less every time, but the energy does transfer, like I said, like a chain of dominoes falling until it gets to the end and until both sides are at the same temperature. Okay, so that is the direction of heat flow. Heat always travels from hot to cold. So if ever on a winter day you've opened the window or opened the door and one of your parents says, don't keep the door open, you're letting the cold in, that's technically incorrect. What you're doing is letting the heat out. Heat energy travels. Cold does not travel. It's always heat because heat is energy. Now consider this case. You have some kind of an object in the middle that will act as a conductor of heat between a hot object and a cold object. The hot object is 100 degrees Celsius and the cold object is 20 degrees Celsius. So of course, the heat energy is going to flow from the 100 degrees Celsius object to the 20 degrees Celsius. This is an example of conduction because all of the objects are touching in order for the heat to transfer. Now, as time goes on, the 100 degrees Celsius object will get cooler and the 20 degrees Celsius object will get warmer. So now we have 80-40, now we have 60-60. Now, once both objects are at the same temperature, this is when the transfer of energy stops and everything is what we say to be in thermal equilibrium. No more transfer of heat. Finally, convection. Now, there's a lot of slides on convection, and I'm actually not going to spend a lot of time on it. So we are going to have quite a discussion on this later on in our class. So that's why I don't want to spend too much time, but I'll give you all the opportunity to read through them, to do some research. I'll go through them really quickly, but I'm not going to spend a lot of time, especially on mantle convection. But convection means you need some kind of a fluid to move around, or you need some kind of medium to transfer heat. And as we'll see, you can actually even have solid objects undergo convection. That's how you end up with things like tectonic plate movement, the formation of mountains, and volcanoes. Now, for those of you who know a little bit about thermodynamics, you would know that hot air rises and cool air falls. Okay? So something like this. Now, if you have hot air rising and cool air falling, eventually you get a cycle. Because when the hot air rises, it cools down and then it starts to fall, which warms up. And, well, this is a current. A current is a cycle. And these currents in nature drive many interesting physical phenomena. For example, the convection of air currents can create something like thunderheads. These are very special types of clouds. This would be an example of atmospheric convection. Another example of convection would be a nuclear detonation. Okay, so you have a lot of sudden energy going up, and, well, the nuclear fallout is what you really have to be careful of. That's going to be the current coming down. Oceanic convection currents. Okay, so there are a lot of very complex ocean currents. Again, I won't get into that. If one of you wants to get into that in your discussion, that's completely up to you. Solar convection, sunspots and flares. So this dark spot here on the surface of the sun is what's called a sunspot. It is a cooler region on the surface of the sun and a region of very high magnetic field activity. We'll learn all about magnetic fields mostly next year. We'll learn a bit this year as well. So as the amount of magnetic activity on the surface of the sun increases, it gets more and more sunspots and reaches something called a solar maximum. Now, out of these sunspots, you have these enormous, magnificent displays of energy release called coronal mass ejections. Some of these are solar flares. Just beautiful. Another example of convection. Mantle convection, plate tectonics, right? We have a lot of different plates around our Earth. Okay, you can see one plate going through California there and British Columbia. That's why they have a lot of earthquakes. They're on a fault line. If you live near a fault line, it's possible that you can feel very, very strong earthquakes throughout your lifetime. Now, again, I won't talk about this too much. I'll let whoever's doing this go over this in the discussion because it is actually very interesting. I'll talk a little bit about this though on the left. This is a diagram of Pangea. Some people call it Pangaea, so however you like. But essentially millions and millions and millions of years ago, all of the continents were squished into one solid piece of mass. Now, what led scientists to actually believe that this is happening? Well, there's two things. One, the continents are still moving today. Now, they're moving very slowly, and when I say very slowly, I mean I cannot underestimate that. They're moving very slowly, but at the same time, dinosaur fossils provided huge evidence of the fact that these continents used to be together. Today, Africa and South America are very far from each other. But when they looked at dinosaur fossils discovered on the eastern seaboard of South America and the western side of Africa, they found that it was the same type of dinosaurs. And those dinosaurs couldn't have crossed across the huge oceans. So that meant that these two pieces must have been connected at some time. Not to mention the actual puzzle pieces. They fit quite well if you look at their shape. Okay, so there's a lot of information on these slides about plate tectonics. Not going to get into that, not going to test you on that. It is quite interesting. NGSS, this is the next generation science standards. This is something in the States, so don't worry about that. This slide actually discusses how plate tectonics work with mantles and the crustal plates. Again, if you are the one who chooses to talk about this in your discussion, you can do the research on it. But there is some information here on the slides as well, which you can use. Again, there's more here on plate tectonics. It is actually really interesting stuff. I just don't want to spend too much time on it. So we're going to go through this. Okay, of course, these plates can create mountains. They can create volcanoes. Here's Pangea once again. I'm going to skip this. So 250 million years ago, this is what Pangea effectively looked like. There's a nice animation of this on the next slide. So this is going backwards into, well, this year. So it's like a countdown. It's interesting. You can see that the Middle East is moving the fastest. So that's interesting. So that's most likely due to a very strong current. Let me just play that one more time so you can see it. You can see that South America and Africa are connected here. And now Africa and Russia, Europe, Asia, they're all going to connect now. Yeah, so that's pretty interesting. So I'll leave the convection currents for our discussion, but that is it. That is the end of our lesson on section 3.1, thermal concepts.